random constraint satisfaction problems below the spectral threshold.
Thanks, David. Thanks for the invitation. This is joint work with Sleel Shram at Berkeley and Satish Rao. Most of the slides are, all the slides are made by Sleel Shram. It's so good that I didn't feel like I should make any change. But if you find any mistakes, it's probably something I still decide to do. Okay, so what is the talk about? The talk is about random constraint satisfaction problems. So the model is as follows. Let's look at an example. You have random 3 XOR. You have n variables, x1 through xn, and for each triple of variables, or each of the n cube triple of variables I, j, k, you add a constraint with 1 minus p probability. You don't include any constraint between the variables xi, xj, and xk. And with probability p, you include the constraint xi, xj, xk. The product is equal to bijk. So the variables are now encoded in plus minus 1. But if you encode this in Boolean instead of plus minus, if you encode them as 0, 1, this is just the XOR bit of xi and xj and xk is equal to 0 or 1. So it's a random linear equation on the 3 variables, and we sample all the constraints this way. So eventually we have p times n cube clauses, and this is what we define as a uniformly random 3 XOR instance. XOR instance with the p times n cube clauses. Okay, so it's very easy to see that a random CSP with roughly omega n clauses, like linear number of clauses, is unsatisfiable just by simple union bound.
Does that side advance not work?
Oh, it works, yeah.
Oh, okay.
Thanks, yeah. Yes, thanks. So a random CSP with linear number of clauses doesn't work. Has no satisfying assignments just by union bound. So in particular, if you plot the probability of being satisfiable, it drops very quickly at the satisfiability threshold. Okay, there's a lot of work on determining the satisfiability threshold and structure of solutions before the satisfiability threshold. But what we'll be interested in, sort of the uninteresting regime, which is way beyond the satisfiability threshold. So in this regime, where if you pick a 3 XOR formula with that many clauses, it's highly likely it's unsatisfiable. But still, what we would like to do is to be able to certify that any given instance is unsatisfiable. Think of certification as a small verifiable proof, like a sum of squares proof or any algebraic proof that this particular system of equations or constraints is unsatisfiable. So we'll call this problem is the refuting problem. So if you want to state it algorithmically, you would say that you want an algorithm that if you give the algorithm an instance that is satisfiable, it will output 1 saying it is satisfiable always. But if the instance is unsatisfiable, there's a reasonable chance with some constant fraction of the time, the algorithm will actually output that it is unsatisfiable. Okay, but this is if you find this a little bit confusing, it's better to just think of it as a proof that a particular instance is unsatisfiable, and the proof should be small and easily verifiable. So one could ask for a stronger certificate, a certificate that not only proves that every assignment violates one constraint, but proves that every assignment violates a constant fraction of constraints. And in fact, at the number of clauses that we are picking, every assignment only satisfies a really small constant fraction of the constraints. Therefore, strongly refuting the CSP still is a very well-defined problem. Okay, so if you had to refute Gaussian elimination, if you had to refute 3x, or you just use Gaussian elimination. So you just take the linear system and try to solve it by Gaussian elimination, and Gaussian elimination would return that the system is unsatisfiable. However, if you now want to strongly refute it. In particular, if you pick linear number of clauses or more, roughly half the clauses are satisfied by every assignment. Now, if you want to prove that every assignment satisfies at most half plus epsilon fraction of the clauses, then Gaussian elimination clearly doesn't work. And for this strong refutation problem, we really have no algorithms, and it's believed to be computationally intractable. In fact, in some sense, the planted version of this problem is known as the learning with errors version, where I give you a 3 XOR formula, which is random, with just the guarantee that there exists one assignment that satisfies, say, 90% of the constraints. And the goal is to find the assignment that satisfies 90% of the constraint. This is this is related to a very well-known problem called learning parity with noise. And this is considered computationally intractable, in cryptography and so on. And it's a very fundamental problem for computational intractability, because in recent work, people have used hardness of this problem towards showing hardness for computational learning. In improper learning, and it's a very nice question. Okay, so now we are looking at strong refutation of 3 XOR. So what do we have? Well, as you can imagine, as we add more clauses, the problem of refuting gets easier because there are more contradictions in the system. And if you sort of look at what are the algorithms that we know, the algorithms that we know is, firstly, in 2 to the n time we can refute all 3 XOR systems just by going over all the possible assignments and checking that each one of them satisfies the less than a half plus epsilon fraction of the assignments clauses. But once the number of clauses is more than n to the 3 halves, then you can use spectral techniques to get a polynomial time algorithm for strong refutation. And this is work by Krivilevich and others. And our work is really sort of an interpolation between the two. We find an algorithm whose runtime decreases as you increase the number of clauses. So in particular, if you had n to the 3 half clauses, you would have a polynomial time algorithm. But if you had n to the 3 minus delta over 2 clauses, you would have a refutation algorithm a strong refutation algorithm that runs in time 2 to the n to the delta, okay, and certifies that it's only half plus epsilon satisfiable. So this is our main result. And in terms of lower bounds, it is known that for weak refutation, which is just refutation, there are several lower bounds in several proof systems. But probably the closest result to our work is the sum of squares lower bounds. So there are sum of squares lower bounds by Grigoriev and Schoenbeck, which exactly match the algorithmic result that we obtain, up to, of course, log factors. Of course, the scale is it's sort of a very strange scale. We are looking at the log of the log, and it's linear over there. So it's in the double exponent that we have a linear. But yeah, and so our algorithm is, of course, as you can imagine, is a spectral, or you can think of it as a sum of squares SDP relaxation for the problem, and we prove that sum of squares SDP of a certain degree can certify that the problem is infeasible. Okay, so that's the main result. Yeah, all right. So here's the outline of the rest of the talk. So there are essentially 3 parts to our paper, but to go from CSPs to the final algorithm. But the first part is really just sort of there's a very simple way to convert any constraint satisfaction problem into an XOR problem, and So in particular, what this implies is our results that we showed for I showed for XOR problem also hold for all constraint satisfaction problems, all random CSPs. Okay, and then then I'll show you how to reduce from XOR to this natural algebraic real valued optimization problem called the tensor norm, which is a very clean problem, and then most of the action is in the tensor norm problem. Okay, so let's set up some notation. So firstly, we have matrices, they are indexed by entries aij's. You have n by n matrix, then the ijth entry is aij. But a tensor, for us it will only look at order 3 tensors, and order 3 tensor is like a 3-dimensional array of numbers, and you have t ijk is the ijkth entry. Okay, so this is what tensors are. And so what is the injective tensor norm? Injective tensor norm is a generalization of spectral norm. So for a matrix, the spectral norm is just the maximum value of the quadratic form defined by the matrix on the unit sphere. Okay, and for a tensor, it's essentially the same definition. You look at the degree 3 homogeneous polynomial given by the tensor, and you try to maximize it over the unit sphere, and that number is called the injective tensor norm. Okay, but these two numbers are look very similar, but computationally they are very different. So for a matrix, it's really easy to compute the spectral norm, whereas for a tensor, computing the injective tensor norm turns out to be intractable. Okay, and we'll use this notation x tensor 3, which is just if you have a vector in R, then x tensor 3 is just a n cube long vector where the ijkth entry is xi, xj, xk. Okay, yeah. All right. So now how do we encode a 3 XOR instance as a tensor norm problem? It's very simple. So recall that in a 3 XOR instance you have variables x1 through xn and constraints xi, xj, xk equal to bijk, where bijk is plus or minus 1. So what you do is you put all the bijk's in a tensor, and you look at the degree 3 polynomial associated with the tensor, and of course you can see that if the constraint xijk, xi, xj, xk equal to bijk is satisfied, this number is 1, otherwise it's a negative 1. So therefore maximizing this is equivalent to maximizing the number of satisfying assignments, satisfied constraint. And so therefore, just with the right normalization, if you normalize this polynomial appropriately, you can see that this is this optimization problem can be transferred from +1 -1 to the n to the unit sphere, because with the right normalization, +- 1 to the n is all the points, all the Boolean points +- 1 to the n lie on the unit sphere. So just maximizing the polynomial over the unit sphere is a relaxation of the CSP. So from now on, we'll just look at the injective tensor norm problem. So you have a 3 tensor or a 4 tensor finally, and then we just want to maximize this degree 4 or degree 3 polynomial on the unit sphere. Okay, and basically all the parameters are work out exactly as you expect, and a result for the injective tensor norm gives you a corresponding result for 3 XOR. Okay, so let's.
So here, actually, IFX is the number of satisfied minus number of
unsatisfied. Yes.
But because you do just one strong refutation, you just want to show that this is smaller than 1.
Yes. Thanks. Yeah. So really, this is I of x as I defined is the number of sat minus the number of unsat, and essentially what is going to happen is for every assignment we'll satisfy exactly half of them. So this is actually going to be a lower order term compared to the number of constraints. The I of x is going to be a lower order term. So really just upper bounding the value of this, saying that this value is small compared to the number of constraints gives you the lower bound on the. Yes. So okay. So now our goal is just bounding the tensor norm. So actually, if you have to do this for 3 XOR, the tensors that we get are sparse because they have only n to the 3/2 non-zero entries in on n cube entries. But for this talk, let's just concentrate on a slightly simpler setting. Let's say you just have a dense tensor. So you have a 4 tensor. So it's a n to the 4 4-dimensional array of numbers, each entry being random plus minus 1. Okay, so let's just look at this problem, and we want to maximize the degree 4 polynomial on the unit sphere. Okay, firstly, this a similar independent result for 4 tensors was obtained by Bhattiporlu, Guruswamy, and Lee. Okay, so let's just see what the norm of a 4 tensor should be. What do we expect? So if you take a 4 tensor, then or basically any tensor, you can show by a simple union bound that the injective norm of the tensor is order root n. Okay, so the injective norm of the tensor is order root n, and what we are interested in is actually proving an upper bound that gets as close to root n as possible. Okay, that's our goal. So we take a random 4-dimensional array of numbers. We want to prove that prove an upper bound on the value of that polynomial on the unit sphere. So let's see how to do this. So the first one, let's look at the simple spectral algorithm for this. So what we have is a 4-dimensional array of numbers. Okay, and our goal is to maximize this in the unit sphere. Prove an upper bound for this. One can flatten 4 tensor into a matrix which is of size n squared in each dimension. N squared by we can flatten a 4 tensor into an n squared by n squared matrix. Okay, so this is a natural thing to do. And again, since if the entries of the 4 tensor are random, the entries of this matrix are again IID random. Okay, so now for any unit vector x, if I look at the polynomial given by the tensor, I can write it as a quadratic form associated with this matrix. So the quadratic form is just apply the vector x tensor 2 on both sides, which is of dimension n squared on both sides, and then you get this. The key point is if x is unit vector, then x tensor x is also unit vector. Okay, so what that means is this number x tensor x a x tensor x is upper bounded by the largest eigenvalue of this n squared by n squared matrix. Okay, and now this n squared by n squared matrix has each entry being IID plus minus 1. Therefore, you get an upper bound of order n. So we wanted to prove an upper bound of square root n. We got an upper bound of order n. But this is an efficient algorithm in that given the matrix, one just computes the largest eigenvalue, and that gives the that shows the upper bound. Okay. So now the question is, how do we improve on this upper bound? So there's a gap between n and square root n. Our goal is to use more running time and get a better upper bound. So the problem here is really this: when we looked at the degree 4 polynomial in x and then went to the quadratic form in y, which is an n squared dimensional vector, there was the relaxation was too much. So, or more specifically, if you look at this n squared by n squared matrix, it's a matrix with random plus minus 1 entries. Now, if you look at the eigenvector of that matrix, the top eigenvector of that matrix, the top eigenvector of that matrix will be an n squared long vector. Okay, but of course, it will not have the form x tensor x. So it will probably be a fairly random vector. In particular, if you look at x tensor x, it has the following property. If I look at the ILth entry, ijth entry, and lkth entry, and ikth entry and jlth entry, their products are the same, because if you have a vector which is x tensor x, the product of this and this is the same. Whereas if you look at an arbitrary n vector of length n squared y, then these two are not equal. Okay, so now our goal is to somehow use this symmetry of the solution that we are looking for. In particular, we want to say that of course the largest eigenvector of A is n, but an eigenvector that needs to satisfy these additional constraints on it will have a smaller value. Yes.
So maybe not directly related to the talk, but something I got curious about for a while, which is like for in general, is there a class of tensors four tensors in which like this upper bound is tied for some specific existential maybe basis? You know, for any like basis, you can make it like the n square by n square kind of things, and is there any this kind of study?
You. In the sense, you want, is there a class of 4 tensors where the top eigenvalue or has this structure automatically?
For some basis of the n square by n square decomposition.
Right. So you're given the basis and you're asking which is there a 4 tensor for which?
Or actually, it's like independent. So for any like
it's basis dependent, right?
I mean, given a 4 tensor, right? There are different ways to decompose it into n square by n square.
Mm-hmm.
You mean, but you mean just like how you choose to arrange you can sort of tile the slices of the tensor differently.
Different like basis to tile.
Okay. So you're asking is there a different tiling for which?
Yes. Say that without worrying about computational complexity,
Mm-hmm.
let's enumerate over all kinds of bases, and then try to compute this like the eigenvalue thing for that matrix.
Ah.
Yeah, I think it's basis independent. But I mean, especially if this guy is symmetric.
No, but it might
No.
depend on how you. If A is actually symmetric, then there's there's only one unfolding.
Oh, really?
If A satisfies 4y symmetry, I mean,
4y
the
symmetry.
only things you can change when you unfold A to a matrix, you can permute. You have coordinates I, j, k, and l, and you can apply a permutation that moves those 4 around.
So does it have to be the
Yeah, you could do even if you did a basis change.
something like a more unitary transform?
Yeah, even if you did a
Unitary transformation has to preserve the fact that
X is a
stays unit vector.
and then it's an operation on all the 4 dimensions of the tensor.
So maybe it's just but I think the spectral bound is reasonably tight if A is a low rank tensor. That would like a random low rank tensor. That would be one class of tensors. The spectral bound is tight.
And the decay is just the rank, or like the gap is just the rank, or
No, the gap. There's no gap.
No. If you let the rank increase from 1 to n, the bound will decay smoothly with that, right?
I think the rank is the most n. There's 4 tensors, so the rank can be larger than n.
Sorry, 1
Mm-hmm.
to n squared.
Once the rank is larger than n, then there will be a gap, and it probably will behave.
oh, you're saying if rank is less than n, there is probably no gap.
Okay. Then after that, you
Oh, that makes sense. If it's random, if the vectors are like
Mm-hmm. Okay. Okay, so it's good. So now the question is, how do we exploit this fact that our vector y must have these symmetries? Basically, imagine if this n squared by n squared matrix had this top eigenvector v, which has the symmetries, which is basically we're looking for an eigenvector which is a tensor product of itself, like it's x tensor x, which are the form x tensor x. So imagine our matrix itself has the form that there is a v tensor 2 whole squared, which is the correct eigenvector, and then there is this the rest, which is like a noise. Okay. Then, in some sense, the point is the signal satisfies symmetries, as we observed. The solution we're looking for satisfies certain symmetries, whereas every other random vector does not satisfy those symmetries. So if we average the entries of the matrix over the symmetries that we expect, then we should kill the noise and amplify the signal. Okay, so that's our goal. But if you look at a 4 tensor on its own, there are not that many symmetries, and in fact, if you start with a symmetric 4 tensor, you really don't get anything by averaging, because A itself will have the symmetries. So if you average A according to the symmetries, you really don't get anything. But we can look at higher order tensors to get more symmetry. So here's how one can do it. So imagine we took our objective function that we had. The objective function we had was just inner product of A with x tensor 4. We squared it. We squared the objective function. Then the problem of maximizing is essentially the same. So what that does to the 4 tensor is, in some sense, you have a 8 tensor. Okay. Alternately, if you look at it as a matrix, our original matrix was our 4 tensor. We thought of it as an n squared by n squared matrix. If you tensor it twice, now you have an n to the 4 by n to the 4 matrix. Okay. So we have an n to the 4 by n to the 4 matrix, and then again we can upper bound it by the square of the injective tensor norm by the spectral norm of this tensored matrix. Okay, but the key is, once we tensor, we expect more symmetries, because if you look at x tensor 4, it has more symmetries than x tensor 2. So therefore, we expect to be able to average more. So that's our goal. So if you take a random symmetric tensor A and look at its tensor, A tensor 2, it won't have certain symmetries that you expect of the vector x. For example, if you just look at a vector x and you look at x tensor 4, if you look at the product of ABij CDKL, ACij BDKL, these entries are just the product of those 8 entries of x. So these two have to be equal. Whereas if you just take a random matrix, a random 4 tensor, then this is a product of 2 random plus minus 1 numbers. This is a product of 2 other random plus minus 1 numbers. They need not be equal. Okay, they won't be equal. So we are exposing the fact that this A actually doesn't look like a fourth power of a single vector, or A doesn't align with the fourth power of a single vector, by seeing that A does not have certain symmetries. So we're going to exploit this, and we're just going to look at A tensor 2, and we allow ourselves to average over the symmetries of the A tensor 2. So here's a formal notation. We take A tensor 2 as a matrix. Now every row is indexed by 4 elements. So we can permute the 4 elements in arbitrary way, and we can permute the columns in column indices in an arbitrary way. So let's pick 2 permutations, pi and sigma, on 4 numbers, on 4 indices, and then you can look at the A tensor 2 with that permutation applied to it, and then we average over all possible such permutations. So in particular, if you look at the averaged matrix and you look at its A, B, C, D, I, J, K, Lth entry, it's actually 1 over 4 factorial whole squared times all these different entries from A tensor 2. Okay, it's sort of an average. And so why should this help? Well, the point is, now in the averaged, if in the original tensored matrix A tensor 2, every entry is plus minus 1, but in the averaged matrix, it's every entry is an average of 4 factorial whole squared entries from A tensor 2. So therefore, the magnitude of every entry is 1 over 4 factorial times smaller. Because of cancellation, it's going to be smaller, and therefore you expect that if you look at the spectral norm of M instead of spectral norm of A tensor 2, the spectral norm of M will be smaller by a factor, which is like 4 factorial. Okay, so we get a small improvement, like the upper bound that we prove is improved by square root of 4 factorial. Okay. Okay, but we still have a sort of a long way to go, right? Because our gap was between root n, and now we want to average over the symmetries, but already we got this improvement, which is we have our improved bound is n over square root of 4 factorial. Okay. And if we want to get better improvement, what we should do is we should actually look at our objective function, raise it to the kth power, and then average over all its symmetries. Okay. So that's what we'll do. So let's look at, if you look at A tensor K, you raise the n squared by n squared matrix to the kth power, and then you average over all the k factorial permutations for pi and k factorial permutations for sigma. Okay. Now again, the same argument, you'd see that each entry of this averaged matrix is an average over roughly k factorial, which is roughly k to the k over 2 or k to the k IID plus minus 1 random variables. And so, I mean, these are not IID, but they are plus minus 1 values. So the average will be of the magnitude 1 over k to the omega k if we actually did this thing, and then the spectral norm will be improved by k to the omega k factor. Okay. And if your upper bound on the kth power of the spectral norm decreases by k to the omega k, the actual bound decreases by 1 over k factor. Right. So the actual bound is the kth root of the spectral norm of this matrix M, and that improves by 1 over k factor. Okay. So that's the simple idea. You just take the n squared by n squared matrix, tensor it, then symmetrize it, and use the spectral norm as an upper bound. And clearly, as you increase the order of the tensoring, the runtime increases because we have to compute this larger and larger matrix each time. Okay, that's the algorithm. Tensor it k times, symmetrize, compute M, and then take the kth root of the spectral norm. Okay. And the runtime is n to the order. Okay, so I mean, the first part is clearly true, that the injective tensor norm is upper bound by the kth root of this. The really interesting part is how do we prove that we get this k to the k over 2 improvement when we do this averaging. Okay. And so earlier we did this intuitive argument where we said, since we are averaging each entry by k to the omega k, by k factorial roughly, the magnitude of the entry should become 1 over k factorial, and therefore the spectral norm should be better. But the problem is, unlike the original matrix A, which had IID random variables, the entries of the matrix M are polynomials, low degree polynomials of IID random variables. They are correlated with each other. They are not IID and uniform and random. And so you need some work to actually prove that the spectral norm drops when you do the averaging. And of course, you need to prove the spectral norm bound anyway from. Okay, so that's the goal. So we need to prove some sort of matrix concentration to say that if you take this specific averaged matrix, its top eigenvalue is at most n over square root k. And the way we'll prove this spectral norm bound is by a very generic method, which is a well-known trace method. If you have a random matrix and you want to prove that the spectral norm of M is at most t with high probability, you sort of compute expected trace of higher powers of M. So you compute expected trace of M to the 2L, and that immediately gives you an upper bound on the probability. Okay, so that's good. So now really everything boils down to computing this expected trace. Okay, so we just want to compute the expected trace of M to the 2L, where M is this averaged matrix that we had. Okay, so I'm going to explain how this given argument as to how this is done, but it will be sort of in a couple of steps. First, let me sort of recall how these things work for adjacency matrices of graphs. So basically, what we are dealing with over here is it's sort of a hypergraph, because we had a 4 tensor. So our entries of the tensor were indexed by a, I, j, k, l. So you can think of it as a 4 uniform hypergraph. But so therefore the entries of M are functions of edges of a 4 uniform hypergraph, random 4 uniform hypergraph. But before we go there, let's just start with graphs and work our way through. Okay, just to set up notation. So for example, if you have a random matrix B, okay, then if you look at trace of B to the L, if B, think of random matrix B where it's like a random graph, trace of B to the L is the number of ordered closed walks of length L in G in the matrix B. So it just so trace of B to the L just counts the number of closed walks. Okay, so computing trace B to the L is just really a counting problem because of this. So, and if your entries of the matrix are random variables which are taking plus minus 1 values, then if you look at the trace of B to the L, it's a polynomial in those random variables, which is trace of B to the L is sum over all closed walks of length L of the product of the edges on the walk. Okay, so it's really this it's a polynomial of these random variables given by this. So what that means is if your random variables are plus minus 1, then you can actually compute expectations very easily. So if you look at expected trace of B to the L, that will just become the number of closed walks by linearity of expectation. It's a sum over every closed walk of the expectation of the product of the random variables there. Now if these are IID uniformly random plus minus 1 entries, then if you look at any monomial which is a product of a bunch of Bij's, its expectation is going to be 0 unless every variable appears to an even power. So if Bij appears to an odd power in this monomial, then its expectation will be 0. So therefore the only terms that survive when you compute expectation are terms where every edge ij appears an even number of times. So therefore computing the expected trace of B to the L for a random matrix with random plus minus 1 entries is really exactly equal to the number of closed walks where every edge appears an even number of times. Okay, so that's it. Okay, so now this is what happens for trace of B in a random IID matrix. Now what we have is this slightly more complicated thing where we take this matrix A and tensor it. So let's see what tensoring does. So if you had a random matrix B whose entries are IID random, you look at B tensor K. Clearly the indices of B were 1 through n. Indices of B tensor K are K tuples 1 through n. So indices are single vertex, where the indices of B tensor K are multi sets of K vertices. Now if you look at a term, an entry of B, it's just an edge Bij. An entry of B tensor K is like a matching. It's a product of Bij for edges ij in this matching. Okay, so in particular, if you look in trace of B to the L, we were counting closed walks. In trace of B tensor K whole to the L, we are counting the number of structures that look like this. It's sort of K matchings going around these L K tuples, and these matchings don't necessarily have to. So it's sort of K disjoint cycles. It's K disjoint cycles, but what we are counting is the number of such structures where every edge appears an even number of times. Okay, that's what we are counting when we. Okay, so now we are ready to go to R matrix. So R matrix is actually pretty, it's pretty simple given where we are. So now our matrix has entries, as I said, from a 4 tensor, right? So in particular, it's better to talk about hyper edges instead of edges, because the indices are actually 4 tuples. So instead of Bij's, now we have hyper edges. Okay, And now what does tensoring do? Right. So again, tensoring, the indices blow up. So you, instead of indexing, the matrix A was indexed by pairs because it was a flattening of a 4 tensor. A tensor K is indexed by 2 K tuples of vertices, and instead of a single hyperedge, you have a K hyperedge matching. And if you look at trace of A tensor K whole to the L, it really looks like this. It's sort of a hypergraph where it looks like this. And so expected trace of A tensor K whole to the L is really just the number of such structures where every hyperedge appears an even number of times. Okay. If we could count it, then we would get bounds on this. So that's it. Okay. Okay. But then we do one more operation, which is we take this A tensor K and we average it over all possible permutations of the row and column indices. So what that does is, if you had an entry of A tensor K is a hyperedge matching like this, right? So Mij is going to be an average over all possible permutations of I and j. So what that does is it does this. Over the same tuple of vertices I and j, you try every possible hypergraph matching, and you average the monomials corresponding to that. Okay, does it make sense? So that is an entry of Mij. Okay, so now we have what is an entry of Mij. It's just average over every possible choice of hypergraph matchings of the corresponding monomial for the hypergraph variables. Yes.
Are you permuting the rows and the columns with the same permutation?
No, sorry, it's actually different permutations. Yes, yeah, they're independent permutations. Yes, yes. Thanks. Okay, so this is the entry of the matrix. So now we can look at what's the final expression that we care about. We care about expectation of A of trace of this matrix, and that corresponds to sort of closed loops in this hypergraph. So let's see what is the structure. You sum over every possible choice of the vertices. So let's just first fix the names of the vertices in all of these columns, in all of these 2k tuples. So there are 2k times L, 2L vertices. Let's just fix them first, fix the names of those. Okay. So this I1 through I2L are these, I1 is this set of 2k vertices. Okay, we are fixing the names of all the vertices in this 2k columns. We are counting all hypergraphs, so we are doing that first, and then we are for every possible hypergraph that you could draw on these things, you have a term. Okay, but so that's exactly what we have here. But this term, when you take expectation, becomes 0 if some hyperedge appears odd number of times. Okay, and our goal is to compute this entire quantity. Okay, but there's one way to sort of think of this as a random experiment. So let's think of this as a random experiment. First, you fix these 2L columns, I1 through I2L, as I said. Okay, if you have fixed these names of the vertices, you already fixed this, and then because of the averaging, you're essentially picking a random hypergraph given the vertices. So imagine we picked a random hypergraph, meaning these hyperedges. You match up each layer to the next layer randomly. Okay, and if you get an even hypergraph where every hyperedge appears an even number of times, that hypergraph survives. And if you get an odd hypergraph, it doesn't survive. So it really just, once you fix these L tuple, 2k tuples, it's really just the probability over random choice of this matchings that the hyperedge is even, hypergraph is even. Okay, that's really what you want to bound.
What's the expectation of the matchings and not the sum of them?
It's an expectation over matchings because our matrix M is sort of an average over the different hypergraphs.
That's the average over
Yeah, say this expectation is coming because of the average over the hypergraphs, whereas this is the sum, which is just the names of the vertices. So, so imagine you just fix the names of the vertices generically. It's some generic, think of generic vertices names for the vertices, and then you're picking the hypergraph at random and asking the probability. Okay, and this is what we want. This is exactly the thing that we want bound. Okay, okay, that's our goal. Okay, and let's see how this is done. It's not too complicated. There's actually a fairly clean way to organize the calculation. Okay, so this looks fairly complicated right now, but let's our goal is to pick this hypergraph at random, and what's the probability that ask what's the probability the hypergraph is even. Okay, instead let's do the sample the hypergraph in 2 steps, sort of to make the computation easier. First, we have these tuples fixed. Let's first pick a matching, random matching, just graphs, just the edges that form a random matching between every neighboring layer. Okay, once you've picked a matching, to get a hypergraph matching, we sort of have to match the edges in each layer. So we take 2 edges at a layer and match them together to form a hypergraph. So this is how we can sample a random hypergraph. Okay, so eventually we only care about the probability that every hyperedge appears an even number of times. Okay, but actually it turns out that it's easier to think of the quantity where not just the hyperedge appears even number of times, but the edges that we chose first also appear an even number of times. So we're interested in this quantity where just probability the hyperedges are even, but it turns out that it's easier to think about the case of probability edges are even and hyperedges are even. And but this seems like a this seems this seems like a cheat. We actually wanted to prove an upper bound on this, but it turns out that they are within an exponential factor of each other. It's not that hard to prove. Well, the idea is take any configuration where the hyperedges are even, meaning every hyperedge appears an even number of times. Okay, now break the hyperedges into edges randomly. You will get a configuration where the edges are even with probability at least 1/4 to the KL or something. If you just break both the hyperedges, you have 2 copies of every hyperedge. If you break both the copies of the hyperedge in the same way, then the edges are also appearing even number of times, and therefore looking at these 2 quantities is essentially the same. Okay, and the advantage of looking at this quantity is that you can actually break it into a more convenient way. You ask first what's the probability that the edge is even, all the edges are even, and then what's the probability that hyperedges are given the edge is even. Okay. Okay, let's see why this is convenient. So it's convenient partly because you want to sort of reuse things and so on, right? So let's look at sum over all the L tuples, the probability that the edges are even. Okay, there are no hyperedges, just the edges are even. This is you can easily bound to be n to the 2 KL. And why does this? Well, basically because you can just reuse. It's sort of this classical thing that appears in random matrices. Okay, why? Because if you look at now, there are no hyperedges; they're just edges, and you're looking at a random matrix B, and you're looking at expected trace of B tensor K whole to the L. Okay, you're counting graphs and B tensor K whole to the L. You can actually count these graphs by hand, or you can just appeal to the known results on random matrices. You know spectral norm bounds on B, therefore you know spectral norm bounds on B tensor K, and therefore you know trace bounds on B tensor K whole to the L. So it's really so this is the thing. And note that in a graph there is no symmetry. There is no symmetry in a there's no the kind of symmetries that we are averaging on doesn't exist in a graph. Therefore, here you don't get any improvement over n to the 2 KL. There is no denominator. Okay, our goal is to get all the improvement from the other term, the probability that hyperedges are given the edges are even. Okay, so let's look at the probability that hyperedges are even given that the edges are even. So you have some configuration of edges such that every edge appears twice. or let's say twice. Okay, so that's typically what happens. Okay, so now if every edge appears twice, when you group these edges, let's see what's the chance that the hyper edge also appears an even number of times. So there are two edges AB and CD. Firstly, they have to appear in the same layer, because otherwise you can never get back AB, CD. Moreover, even if they appear in the same layer, right, first you pair AB with CD, and then you go ahead, and when you're pairing that layer, there's roughly a 1/k chance that you will pair AB with CD, right. The chance that you pair AB with CD again is 1/k, and if you don't pair AB with CD, then this hyperedge ABCD doesn't have its partner, and it will remain odd. So the probability, and this choice is sort of true for every hyperedge that we make. Every hyperedge we make on every layer essentially is one occurrence of a pair of edges, and there's another occurrence of a pair of edges somewhere, and we have to match them up exactly at that point. So really the probability that hyperedge is even, given that edge is even, is like 1/k to the KL. Like there are KL hyperedges that we pick, and each time it's like 1/k chance. So okay. So now we can go back to our calculation. So we already saw the probability that the hyperedge is even is within exponential factor of the probability that edge is even and hyperedge is even. Okay, and firstly, we saw that the sum of the probability that edge is even. This is just a classic matrix, random matrix bound, is n to the 2kl. So here there is there's no improvement due to averaging. All the improvement due to averaging comes because of this part, which is a probability that hyperedge is even given edges are even. You get a 1/k to the KL factor. So this is really is the this proves the bound that we wanted. Okay, so okay. So and as you can recall, once we have the tensor norm bound, we get the corresponding thing for CSPs.
Okay, how do you get the polynomial though? Because it seems that you need to take it to the very large power.
Oh, the polynomial time algorithm. Oh well, the polynomial time algorithm is the one which we discussed first, where you didn't do any symmetrization. Okay. The thing that with sufficient density, without any symmetrization, just the spectral norm bound gives you the right answer. But you need symmetrization only when you have fewer and fewer clauses, and so really when you have a really sparse instance, that's when this symmetrization really helps, but it runs in time exponential, like the.
I mean, I'm just not seeing how this 2 to the n to the epsilon comes from the analysis.
The 2 to the, so basically, right. So let's see. So we had to go from n to square root n, right? Yes. So to go from n to square root n. So we had a polynomial time upper bound of n easily, and now if we discover that if we run in time n to the k, because if you symmetrize it k times, the runtime is roughly n to the order k. If you run in time n to the k, you can actually prove an upper bound which is better, n over square root k. So if you pick k to be anything, so between n and 1 and n, you get better and better upper bounds with runtime which grows with k. So if k is n to the delta, then you get n to the 1 minus delta here, and here you get n to the k runtime. So if k equal to n, if k is equal to n, you prove the tight upper bound, which is root n, which is the right answer for a random 4 tensor. The injective tensor norm is root n, but the runtime will be 2 to the n.
I think one confusing thing is that you use k on the plot. You use it for the arity of the constraint.
This k is different. That k is different from. Here the k is the symmetrization, the number of times you symmetrize. Here it's yes. Did it make sense? So right. Yeah, okay, I guess one thing which I didn't mention is how the density affects the bounds that you want. Yes, yeah, so how does the density affect the bounds that you want? So basically, as the density increases, the gap between, suppose the density, suppose you have more clauses. Essentially, if you have m clauses, then you can roughly satisfy square root m, half plus square root m clauses.
But you're not trying to get the square root m, right?
You're not trying to get square, but the point is, so the gap is square root m, okay, between satisfying 0.9 fraction and in terms of the value of the polynomial, the gap is between satisfying 0.9 fraction of the clauses versus satisfying 0 fraction. What is truly possible it grows as the number of clauses increases. So you are actually solving a weaker certification problem for the tensor problem over here. Like as you increase the number of clauses, the bound that you want for the tensor norm is weaker, and that's why and that's the reason why you get this trade-off with the number of clauses versus the runtime. Yeah, right. So yeah, so the issue, yeah, in tensor norm there is no density. The problem that I described, really there is no density. It's really a better bound on the tensor norm, but over here, because as you change the density, when you convert the problem into tensor norm, you're proving weaker and weaker bounds.
But I mean, so certain bounds on the tensor norm translate to strong refutations for certain densities.
Right. Yes.
And it's some kind of linear dependency. What's a
Yes.
dependency between the tensor norm bound and the density that you can?
Yes. Yeah. Yeah. Yes. Actually, I should have gone into that. Yeah. It's a subtle point, and in fact, there's like I'm also hiding a lot of things under the rug. The fact that the CSP is sparse really messes up all the things that we did so far, in the sense that the trace norm bounds and so on, you have to be a bit more careful, because it's like a random matrix with whose entries are very sparse. It's like a sparse random matrix, and the problem with sparse random matrix is in the expectation calculations that we did, we would just count the number of terms because all terms are roughly the same order of magnitude. But when that's because all the random variables are plus minus 1, all their norms are 1. All their norms are 1. But if you have a random variable whose higher norms are larger, it's ill behaved in the sense that the 2 norm, the 4 norm, the higher norms are larger, then we also have to take into account the number of times each hyperedge appears. If a hyperedge appears many number of times, then it contributes a large magnitude to the term. Okay, and we actually fix that issue by looking at a restriction of we don't look at this entire matrix, because in this entire matrix A tensor K, there will be entries like A 1 1 1 1 1 2 2 2 2, which corresponds to having the same hyperedge repeated so many times, and that's going to be a huge order of magnitude, because if that edge appears with probability p, then you get a large quantity, if otherwise you don't. And so instead what we do is we look at the submatrix where the indices are multilinear, where the subsets are actually have no repetitions, at least the row and column indices, there are no repetitions among them, and over there all the norms can be like this. Calculation all still makes sense to a large extent, because you still have in every tuple every vertex appears a constant number of times. Yeah, but the proof itself is by actually counting these hypergraphs, by really actually counting the hypergraphs using encoding technique. You just encode every hypergraph as you ask how many bits do you need to actually encode every even configuration, and
continue to ask essentially the same question. So the sparsity, the m, the number of clauses, actually in the very end you do the concentration. The other one is now the for the matrix concentration bound.
yes,
I
yes.
suspect for the second one, it's not very sensitive, right? The sparsity, or does it actually literally show up twice, and in the very end you trade off and you get this bound?
Yes, I don't think there's a.
So both of them are random.
Right. Sorry, I should. So let's see. I don't. Right. I don't think the sparsity changes the tensor norm cal thing much. Yeah, it doesn't.
Normally, if you have a matrix, if you have a relatively sparse matrix, you still have concentration.
Yes. Yes. Yeah. Yes. Yes. You still can prove these results in the sparse case, except the results, the bounds will be different. But it's still what you would expect from, let's say, a random matrix with that Frobenius norm. It is.
Really? I thought that once you start lowering the clause density of the CSP, that okay, for the situation you described, there are two kinds. There's the kind of vector that you're trying to kill off, like one kind of high quadratic form vector you're trying to kill off. It's non-symmetric. But I thought that once you made the clause density lower, there are actually symmetric vectors. So like V tensor K, which will still give you bad quadratic form if V is not a balanced vector. Right? Once the
Yes. No. Right. No. After. Yes. Sorry.
You have to change something about the.
Yes. After you do the multilinear, like if you look at the multilinear part of the matrix, the P doesn't affect it. Yeah. If you don't look at the multilinear part, I think you can. You can basically you can create a vector which just puts mass on let's say K, one hyperedge, and then if that hyperedge appears, you get all the L2 norm, and no cancellation because just one hyperedge. Yeah, exactly. Yeah, so it's important that you look at just the multilinear part, and over there it doesn't matter. Yeah, that's it. I'm done. And okay. So the only open questions I really want to emphasize is we still don't know the computational interactability or tractability of the following basic question. I just give you a homogeneous degree 3 polynomial over the units and ask you to maximize it over the unit sphere. As of now, there could be a polynomial time approximation scheme for this problem. There's not even a there's not even no pitas hardness result known for this in terms of computational interactability. Quasi-polynomial time approximation scheme. Yeah, there is a hardness reduction which runs in 2 to the root n time, which constructs an instance is 2 to the root n time. And so really don't know whether this problem is tractable or intractable. It's really basic question. Just given an arbitrary homogeneous polynomial, maximize it over the unit sphere. And we don't have good algorithms. The best algorithms achieve an approximation ratio which is like n to the 3/4 or something for degree 3. Okay, I'll stop here.